Alright guys, this is an overview of your model K11 AC/DC power supply kit. You may recognize the image here on the screen. Sorry, a little blurry, but that's a photo of the whiteboard from the classroom. This is our schematic of the power supply itself. And so I just want to give you a review of the different aspects, the different parts of our power supply. So when we plug this in, we're getting estimated 120 volts AC. That's the RMS value of our AC voltage input. And we actually measured that in the classroom. We were getting about 123 volts AC. It comes into a step-down center tap transformer. This transformer steps the voltage down. It is rated for 13 volts RMS at AC, and we actually measured that to find out that we were getting about 17.6 volts RMS at our our output here. So center tap transformer splits the voltage into two phases here. The center tap to ground, and you get a sine wave AC signal on this coil and another one on this coil, and they are 180 degrees out of phase with one another. The center tap allows us to have a more efficient power supply, requires less diodes to rectify that signal and turn that AC waveform into a pulsating DC waveform. If we didn't have the center tap and we just had a fixed transformer here, we would need 4 diodes here to create a bridge rectifier. It's not as efficient of a rectifier circuit. So the center tap allows us to have a more efficient with less components. The diode of the rectifier we know allows current to only flow in one direction, and because of that, and because the signals are 180 degrees out of phase, you end up with a pulsating DC signal. That pulsating DC signal is then filtered by a large capacitor, this electrolytic capacitor right here. We have 1,000 microfarads that is filtering that signal and gives us a small rippled signal. And then that ripple signal is passed into our voltage regulator circuit. That's consisting of these transistors here, this potentiometer right here, and this Zener diode. So the Zener diode is key to the voltage regulation in this particular circuit. Our Zener diode, hooked in reverse bias here, is giving us a reference voltage of 17 volts DC. And then that reference voltage is split over this variable resistor, this potentiometer here, and that allows us to control the base voltage into this transistor right here. This is a PNP transistor. Know that on the emitter side of this transistor, as with every transistor, we're going to see about a 0.7 volt loss. That's because the semiconductor has an internal resistance to it, and so there's always a voltage drop between the base and the emitter of 0.7 volts. But it does allow us to maintain a constant voltage on the emitter here. And in this particular voltage regulator, they're actually utilizing 2 transistors, the second one being a power transistor, and this further helps reduce the current draw on the Zener diode itself, making it a much more efficient voltage regulation circuit. If we only had the Zener diode, we couldn't vary our output, but we could have a nice straight regulated DC signal that could serve very well. At the end of this circuit, we have a capacitor and a resistor that further filters. It basically serves as a load filter for our circuit and further cleans up the signal to give us a good straight DC output. So I'm going to take this and zoom this out a little bit. You may recall our discussion in class as we looked at the circuit. We simplified it into a diagram. This is what's known as a block diagram of our power supply. So you see the sine wave AC input. We are stepping down from a large AC signal to a small AC signal. Because ours is a split transformer, we're getting a fixed 8-volt AC output. We use that to power our little light. We also have our approximately 18-volt that's going on. Now it's controlled by a switch, and then the switch runs through the rectifier. Here's our pulsating DC signal. That pulsating DC signal runs through our filter, a large capacitor there. And so here we see a smaller rippled cascading the tops of these, filling these valleys in. So we take that rippled signal and run it into our voltage regulator, which is made up of the reference voltage from the Zener diode and the potentiometer and the transistor. And then further the load filter, which is made up with capacitor and resistors on the post side of this here. And in the end, we have a nice, efficient DC power supply that gives us 0 to 15 volts on DC output. Now let's take a look at the actual circuit.